Okay, so the participants will not be able to, those who are saying, they will not be able to speak, right?
They only chat, sir.
They will only chat,
Yes,
and
sir.
chat will be visible in.
YouTube, sir.
Okay,
YouTube.
okay, so I think Grishma, you can just keep checking whether there is any question in the chat. Okay. Hello, Grishma.
Yes, sir. But yeah, yes, sir.
Okay. So
Hello.
yeah, so there are five participants, right? Right till now.
Um,
Can you see how many are there?
uh, okay, sir. 1 second. I
Seven, sir. Six,
Seven.
seven.
can see seven waiting. Seven waiting. I can see, but not more than that.
Yeah, but seven waiting, but are they? I hope they are in actually, and they are able to hear us.
Sir, please play your video, sir.
Okay, should I switch on my video?
Yes, sir.
Okay, so you can see me now, right?
Yes, sir.
Okay, so shall we start?
Yes, sir.
Yeah, so welcome those who have logged in for this live interaction, and this is for the MOOC course, which is rerun for the second time, which is electrical equipment and machines finite element analysis. So I am Professor S.V. Kulkarni, faculty at IIT Bombay Electrical Department. And with me today we have Dr. Sairam, faculty from IIT Dharwad Electrical Department. Dr. Grishma, she is faculty NIT Calicut. And we have a special guest and expert, Mr. Swapnil Badgujar, who is also MTech from IIT Bombay, and now he earlier he had worked with Comsol, and then now he's working with John Deere Consulting Company. So he's a expert. He's an expert on finite element analysis and applications. So what I will do is I'll just give a brief overview of this course and why this is important, and then I will request Dr. Sairam, Grishma, and Mr. Badgujar also to share their thoughts. And then we can we get some questions or queries from those who have registered for this live interaction. So this course, as the name suggests, deals with understanding finite element method basics and applications to electrical equipment and machines. So if you take any product industry, low frequency typically, because this course is mainly for low frequency applications of finite element method. So if we talk of an electromagnetic device like transformer, motor, generator, switch gear, relay, electromagnets used in relay applications and all that. So all these devices, when they are to be designed, analyzed, or optimized, finite element analysis comes to great help. And any of these, manufacturing or consulting industries dealing with these products, they invariably have finite element software, commercial softwares like ANSYS, COMSOL, and so many other softwares are there, and like Magnet. So these softwares are regularly used by industry professionals, and if one basically undergoes this course, that person will definitely be more enlightened and informed about power basics and power of finite element method. So this course, basically, if you see the first 10 lectures are on fundamentals of electromagnetics. without sound knowledge of electromagnetic fundamentals, it will not be good to get into finite element method, because finite element method is like, whatever you feed in, you get the output correspondingly. If you feed wrong results, wrong input, you will get wrong results. Or if you get some output, if you are not able to understand or interpret the result, then again it is of no use. So understanding fundamentals of electromagnetics is of paramount importance, and that's why we have devoted like about 10 lectures for this. And I think the course is already underway for about more than, I think, about 2 weeks now, or more than 2 weeks. So I'm sure some of you have been exposed to the first few lectures wherein fundamentals have been covered, and these fundamentals are specifically related to finite element method application. So not all fundamentals of electromagnetics are covered, but specifically those fundamentals which are more relevant to finite element method and the analysis and interpretation of results. All those fundamentals are covered. Then from lecture 11 to almost like 20, finite element procedure are described in detail, starting from 1D, then 2D, and giving codes, explaining the codes in Scilab. We have taken care that we basically use freeware software like Scilab, so that anybody uh, can basically attempt simple coding in 1D and 2D, so that then one can use commercial software with very high confidence. These codes can be used also to one can, even those who are working in academic institutes doing research, as well as those who are working in industry, if they are interested, they can develop two-dimensional codes very easily for magnetostatic or time harmonic problems and electrostatic problems for their standard geometries, and their problems are standard, and then one can actually use those codes also. For complex problems, one has to use commercial software, and for 3D problems, of course, commercial software has to be generally used. So lectures 11 to 20 deal with finite element method and procedures. And then from lecture 21 onwards to lecture 40, you have different applications of finite element method, and the applications, the complexity of application increases as you go from lectures say 21, 22 to 40. Right from say electrostatics to magnetostatics, then time harmonic, wherein there is a time varying excitation is there, then non-linearity, then coupled analysis, coupled circuit field, coupled electromagnetic structural. All those cases are coupled electronic thermal and structural. They are not dealt in that detail. We have just given some hints on that, but they can also be if one has interest, then there are books which can be referred for electromagnetic thermal and electromagnetic structural. Having gone through this course, then it would be easier for the participants to understand multiphysics computations and algorithms, because electromagnetic, that is circuit field analysis, is taken in details as part of this course. So how to solve coupled equations is elaborated in this course. Finally, I think at the end we are also dealing with force calculation, the types of electromagnetic forces, and what are the different methods for their calculation. So I think there is a spectrum of topics that are covered, and I'm sure the participants who have registered for this course would definitely get better understanding of finite element method and procedures, and they would be able to solve complex problems either in the research or in their as part of their industry profession. So I think with this introductory words, I will now ask Dr. Sairam from IIT Dharwad, who did a PhD at IIT Bombay, and he was quite involved in this course. And in fact, he has given, if I remember correctly, more than one lecture as part of this course. He basically explained the Scilab code uh, as part of this course. So I now request Dr. Sairam to share his thoughts on the importance of this course, and why this course would be uh, useful to somebody who is working either in academic institute, research organization, or industry. Over to Dr. Sairam.
Hello, hello, sir. Can you hear me?
Yes, yes.
Yeah. So, good evening, all. Thank you for joining this live interaction section, and thank you, Kulkarni sir, for this live interaction session. So now I will just talk about 3-4 examples which has helped me during my last 3 or 4 years of my post PhD experience, which has helped me in solving complicated problems during my industry. And these concepts are the concepts that are being taught in this course, or be and then they have helped me in solving some few questionnaires as well. And also by this I have helped some industry professionals in solving their research problems. Now, the first one goes with induction motor analysis. Like if you actually solve for an induction motor in transient analysis, then typically it would take so many number of cycles to go to its steady state. Like if you, all of you may be knowing about RL transient. Like if you have a RL circuit, and if you excite that RL circuit with a simple sinusoid excitation, then it will draw inrush current and it will go to steady state after so many number of cycles. So induction motor is also a kind of an RL circuit only. So if you are exciting that RL circuit with a sinusoid voltage source or a three-phase voltage source, then in FEM simulation it will take so much amount of time for it to go to steady state analysis. So so one of our customers in my previous company is facing the same issue. So then we have came up with a solution wherein we have provided the initial solution for the transient analysis as a frequency domain study. Like in one of the lectures, I think lecture 29 or 30, sir has explained about how you can analyze induction motor torque speed characteristics by using frequency domain analysis. So the solution of that frequency domain analysis, we have provided it as an initial time step to the transient analysis. Then with that small change, we were able to get to the steady state result within a few cycles only. So that has reduced the computational complexity that was facing by our customer in a more drastic way. And that is sort of an example wherein I have used the concept that is being taught in this course for solving a induction motor problem. Similarly, nowadays you might have seen motors like axial flux motor or motors with squeezing and all those things. So for these motors, you have to do definitely 3D analysis. So when you are doing a three-dimension analysis of a motor, then you can't rely only on magnetic vector potential. So in the basics of the course, in the first 9 lectures of the course, sir might have taught you about the difference between magnetic scalar potential and magnetic vector potential, and how and when they have to be used. So basically, with typically all FEM softwares in general will use magnetic vector potential based formulation. But in 3D motor analysis, along with magnetic vector potential, if you use magnetic scalar potential, then the computational complexity will reduce significantly. So that's why some of the softwares will propose a mixed formulation while analyzing 3D models. So even though there all the formulation and everything is there in the simulation software, you have to understand where to apply magnetic scalar potential and where not to apply magnetic scalar potential. For example, you have a lamination sheet, and if you want to analyze the eddy currents in that domain, then you cannot apply scalar potential in that domain. And if you have a permanent magnet rotor wherein you will not have any induced currents, then in that domain you can apply magnetic scalar potential. And also, when you are applying magnetic scalar potential, as sir has explained in one of his lectures, that domain should not enclose any current carrying conductor. So that has to be properly examined before before you start your analysis. So this is one concept related to basic electromagnetic analysis that has helped me in understanding and knowing the procedure of how to solve for a 3D motor analysis. And along with that, generally, if you see one of the lectures on permanent magnet motors, like modeling of permanent magnets. So we generally, if you see any FEM software, they will model the permanent magnet as a linear characteristics. But that does not mean that the magnetic characteristics of a permanent magnet material is linear. So all the engineers or whomsoever are working on the FEM analysis of machines or permanent magnet machines, they will think that it has been approximated as linear, but it is not true. So the difference between the magnetic characteristics of a permanent magnet material, like MH, difference between the MH characteristics and BH characteristics, this difference is clearly explained in this course, and that lecture has been developed by sir by referring to so many fundamental books, and understanding of difference will help you in modeling some of the latest permanent magnet materials, like for example alnico material or ferrite based material, wherein demagnetization characteristics are more predominant. In those cases, you will be requiring these kind of concepts. And lastly, I want to add one important point, in one of the lectures wherein we will be calculating flux linkages of a coil. So sir will be deriving how to calculate. So you have solved your FEM problem, and then you got the flux distribution, magnetic vector potential solution, and all those things. And after getting all these solutions, you have to calculate, let's say you have to calculate flux linkages and inductance. So how can you calculate flux linkage from magnetic vector potential? That has been explained in one entire lecture. Incidentally, in one of the interviews that I have attempted, by one of the interview for a EV company that I have attempted, they have asked the same question to me in that interview. So this kind of settled concepts, even though we have so many number of commercial softwares in the market, to use these commercial softwares, we have to know and understand these concepts. In some critical cases, like normal operating condition motor analysis or transformer analysis is everybody doing, and more or less that part of work is almost like saturated. But nowadays people are working on like something like integrated chargers, or wherein your motor will be a part of a DC-DC converter which will charge the battery. So in that case, the motor will be operating at a switching frequency, at the switching frequency of converter. So in that case, you have to consider the effect of eddy currents in the laminations and all those things. In for such condition, you cannot go with the simply with the solution that your FEM software will provide. You have to incorporate the knowledge of finite element method and electromagnetic analysis to appropriately do that. So similar kind so that kind of knowledge that I have gained in this, I was able to solve one problem, and recently that paper got accepted in one of the conferences. So these are some of my practical experiences which in which I have implemented the knowledge that I have gained from this course in my research and as well as industry career. Yeah, thank you, sir.
Okay, thank you, Dr. Sairam, for your insightful comments. And I would like to again, say that this course actually is, because electromagnetics is generally perceived as a difficult course by students, as well as by teachers, also difficult to teach subject. But as manufacturing sector, develops in India, which is expected now, if we have to really make a mark at the global level, we have to actually, we have to develop our own technologies. So when you have to develop our own technologies, finite element analysis has to be, there is no other option but to, use such numerical techniques. See, what happens is, I would just like to say that in mechanical and civil and aeronautical engineering domain, the finite element analysis is like their bread and butter, because they cannot think of doing any significant analysis without such software. But what happens in electrical engineering, we are taught about circuit courses from semester 1 or 2, and we are happy doing equivalent circuit analysis, and we then lose sight of the space and what is happening in space. And that is the reason that the electromagnetics gets defocused in many colleges and many institutes. That's why students feel that this subject is highly theoretical and it has no practical relevance. But those who graduate and they join some industry, after joining that, those kinds of industries, then they realize the importance of this, course called electromagnetics, and then its applications, and then the corresponding analysis by, numerical techniques like finite element method. So more about that I will tell later if there is some question. Now I'll request Dr. Grishma, who is a faculty at NIT Calicut. She also worked with me at IIT Bombay for her PhD, and her specialization is in the area of power electronics. And I request her to tell more about how such a course, undergoing such a course, is helpful to do research in areas like power electronics. Over to Dr. Grishma.
Thank you, sir. So, good evening, all. So today, I just want to give you an overview, since Dr. Sairam has already given you a brief overview about the rotating machines. So what I thought, I will discuss more about high frequency magnetics. So for power electronic converters, since we are going at higher frequencies, we are more interested in analyzing the circuits. So recently, some applications are based on resonant converters and magnetics for resonant converters. So along with that, one more new area which people are interested is basically the planar magnetics. So with this course, how it can be further used is basically in the design and analysis and optimization point of view. So we one aspect is basically the calculation of losses associated with this magnetics for different application. The other one is basically finding the equivalent circuits. So there are some traditional methods to design the magnetic materials at higher frequencies. But what happens is, like, there is no rules as such for this high frequency design. So what happens is, like, when somebody designs a magnetic transformer for some application, it will be designed for a particular frequency range. And when you basically test the material at that particular frequency, sometimes resonances happen and some ringing will be there. So with this FEM software or analysis, we can actually predict the equivalent circuit. So parameters like leakage inductances or capacitances associated with that. And we can predict at what frequency ranges resonance will come and how we can modify our design further. So one is basically the winding arrangement of this high frequency transformers. We can do some kind of analysis on that. And other is basically the calculation of leakage inductances associated with the transformer. So we are already discussing in some lectures how you can do with the help of commercially available softwares also, and apart from that, analytical calculation. So this can be used directly for newer geometries also. Other than that, planar transformer is also one of the planar magnetics is one of the latest addition to the magnetic field, where when there is a space constraint at lower levels, miniaturized circuits are needed. We some are interested in the planar transformer design or planar magnetics. So how our temperature variations or losses, hotspots in the magnetics can be basically understood from this kind of simulations. So that is about the high frequency magnetics. That's all, sir.
Okay, thank you,
Additional
Dr.
points.
D. Yeah. So depending upon question, then you can come in again.
Yes.
So now it's my privilege to request Mr. Swapnil Vadgujar, who also did MTech at IIT Bombay way back. I don't remember now, maybe 10 years back. And then he worked for some time in Comsol. So I request him to just briefly give his professional career also, where he worked and what kind of experience he gained, and basically tell about his MTech project also, what he did and how that helped him, get a break in company, good, company, and then how it has helped shape his career. And then tell about also about the importance of this course and understanding basics of electromagnetics and finite element method, how that will actually is very much, sort of is a very good value addition to one CV, and is really valued very much in manufacturing, typical manufacturing and the R&D industry. Over to Mr. Swapnil.
Yeah. Thank you, sir. I hope you can hear me there.
Yes.
Okay, great. Yeah, so as sir mentioned, it's been 11 years now that I finished my master's, and from last 11 years, I have been associated with electromagnetic field computation. So as a part of my, everyday job, I get to solve electromagnetic fields for various applications using commercial tools mainly. So yes, as sir mentioned, I was exposed to this field of computational electromagnetics during my master's, and there during my master's, my thesis was on meshless methods. So of course this course is all about finite element method, but there are some alternate methods like meshless methods, and they are applicable in certain applications. They have a limited range of validity. So going through first of all, the course which was offered on computational electromagnetics really exposed me to a broad set of numerical techniques which can be used to compute EM fields, and the application of these fields are are extremely wide. Motors and generators is probably just one example, but you imagine any device around you which carries electrical current, you might see a possibility of using some of these techniques to optimize that device or that design. So yeah, after my master's, based on my project work and my exposure to this area, it was very easy for me to get a job into one of the softwares, which was Comsol. So Comsol develops a similar FEA-based electromagnetic solver. So based on this course, it was fairly easy to get into that company. I spent around 5 years in that company, where I actually saw how Uh, these tools can be used in variety of industries. So it is not just limited to energy and power, industry, like where you talk about energy generation to energy utilization, but these applications can be into aerospace or nuclear or biomedical or even oil and gas. Anywhere you talk about a new product development, uh, I'm sure you will find use of these tools and these methods. So yeah, after that I switched gear and I joined John Deere India uh, as an simulation engineer, and I've been working with John Deere India in Pune for last 6 years now. And given my background in this field, I could easily switch different careers within John Deere itself. So I joined as a sensors engineer. I worked there in sensor development for 4 years. Uh, but since the physics remains same, in any device, it's all electromagnetics that's happening. I could easily switch to a different higher level role, which was into e-machines, electric machines development. So I've been working on electric machines now for last 2 years at John Deere India. So I do believe the last 11 years have been very rewarding for me from career perspective. If you enjoy solving the physics problems every day, if you enjoy those if you enjoy physics and mathematics, this is the career option for you. And to talk more about the industry scenario today, uh, typically in large industries, simulations are greatly valued. In the overall product development process, simulation is a key milestone. So if you're able to build a simulation model for your product, for your process, you have hit that milestone. And that increases the company's confidence in bringing that product to the market. So companies do value simulation work. They are not shy of spending money in simulation tools, computing resources these days. So you can even HPC access, which was not so easy when I started my career, but it's easily available now. Companies are not shy of spending any money in simulation based engineering, because they do realize the value addition. It's not just the product development. Simulation tools are used in various levels, starting from product ideation. If you have a different idea, if you want to try out a new idea, simulation is the first step to see whether that idea works or not. So once it works, the next stage is to design and optimize it. you know Even in that case, you can rely heavily on simulation tools to optimize your product design. And after that, you can neatly test various scenarios, again based on the simulation tools. So product ideation, design and optimization, and finally testing and integration. So simulations can be used in all three phases. Uh, in fact, what I've seen in last couple of few years is electromagnetic simulations are increasingly being adopted in industries. Uh, I come from the automotive background, in my current role. Uh, and the recent trends like electrification and autonomous driving or ADAS based systems, that has really increased the amount of electronics and electric product that go in automotive, which was traditionally a purely mechanical uh, branch. So yeah, with time, I see a large adoption of these technologies, these techniques that you will be exposed in this course. And yeah, there are some latest trends, AI, ML, which also go pretty well hand in hand with these techniques. You will definitely see a lot of exposure when you combine the physics based techniques with the AI ML techniques. That's a different area altogether these days. One more, comment I would make is, the multiphysics part. The real life problems are not single physics, but they tend to be multiphysics. And once you have learnings from this course, I would recommend you to look further into the multiphysics aspects of it. Yep. Yeah. So I think all in all, for me, this has been a very rewarding career, and I hope the same for everyone. Thank you, sir, for this opportunity.
Okay,
Yeah.
so thank you, Swapnil, for your nice comments and highlighting the importance of this course and how that will be really beneficial for practicing professionals as well as those who are aiming to get a good break in some reputed industry. Right. So now actually, since we have had one round of comments by all those who are there here. Now I just saw some comments in the chat box. I could notice three basically questions by those who have logged in. One is some participants are asking whether there will be one more such interaction at the end of the course. Yes, why not if there is a demand from you, and if I would request that there should be some specific, queries and questions, or there should be some demand from those who are registered. If they want to have more discussion or more clarifications on some topic. Otherwise, it becomes difficult for us in that 1 hour what to talk and what not to talk, right? So if there are some specific queries, questions or comments, and if there is some demand that this particular topic should be covered or should be discussed again, in the live session, then we can definitely have one more session at the end. That is one. Second query is about are there some new additions in this rerun course as compared to the first one? No, there are no additions. But if there are again, it depends on the pull from the if there are some suggestions from the participants who are registered for this course that the such and such topic should be covered. They can write to me, and they definitely we can consider adding something if there is greater demand to focus on some topics. Why not? So it will be a good exercise for us also. And there is one more question about, I mentioned in the beginning about low frequency and high frequency sort of split. And then I mentioned that this course is for basically low frequency. So one query is there in the chat box. How do you sort of divide this, low frequency and high frequency? So basically, if you talk about, in electromagnetics, there are two distinct set of researchers. One is low frequency researchers. So low frequency doesn't mean it is only power frequency 50 hertz. Low frequency extends up to few tens of kilohertz or up to say few hundreds of kilohertz. And the dividing line is basically the frequency up to which you can actually neglect the displacement current and radiation effects. We call that as like sort of low frequency, where we may be interested in suppose for example eddy current calculations at significantly higher frequency of say 50 kilohertz. So it is still a low frequency problem, although the frequency may be frequency of excitation is 50 kilohertz. Whereas if you are talking of some microwave device or antenna, specifically which is radiating structure, or it is, allowing power which is, propagated in space and it is channelizing through a waveguide or a fiber optic cable. So then wherein it is mainly the displacement current which basically enables the, wave propagation phenomenon. So there it is distinctly high frequency electromagnetics, and it is altogether a different cup of tea, in the sense the finite element method procedure as such is same, but for example, here we use nodal based element. There mostly edge based or vector elements are used. And the modal propagation is the key aspect there in high frequency electromagnetics, wherein we want to know what modes of propagations are existing and all that. So basically the modal propagation and wave propagation, these are the main things that are part of the high frequency electromagnetics, and it's generally not possible to cover both the aspects into one course, because the priorities are different, the interest of participants are widely different, and it would be just confusing for participants to know the other side of the story. That means low frequency guys may not be interested in knowing how an antenna is modeled. Similarly, those working in antennas stuff, they may not be interested in analyzing transformers or motors or generators. So typically you will see the researchers are also divided into two distinct parts, low frequency and high frequency. So this course is basically for low frequency, and I'm sure there will be some course under NPTEL which will be on high frequency, electromagnetics. Uh, and the parts, those who are interested, they can actually, go for that. So I think I have covered whatever I saw the questions. So Grishma, are there any further some questions that I have missed in the chat box? You are on mute.
Hello.
Yeah.
Sir. No questions in the chat box.
Yes, I think there are some 9 or 10 participants. So maybe
Yeah,
I again request them, if they have some queries, they can put in chat box now. Otherwise, then we'll have to, slowly wind up this session. Yeah, so one question has come. Yeah, now questions are coming. Thermal analysis, ohmic heating losses will be taken care in this course. Yes, definitely. If you see the eddy current analysis of eddy currents, that time harmonic analysis, that will help you to calculate eddy current losses, and eddy current loss per unit volume, which is integral rho j square dB is the expression for calculating eddy loss. Rho j square is the eddy loss per unit volume, and when you integrate over volume, then you will get the total loss. That loss density can be actually given as input to your thermal model. Now thermal model and the corresponding analysis is not part of this course, but those who are interested, they can easily take help of some experts in the thermal area, and then basically in this multiphysics software like COMSOL, ANSYS and others, there will be tutorials how to basically input the heat input. Heat input is in terms of eddy currents. So you need to then understand and know how thermal FEM analysis is performed. So you can appreciate that it is not possible to cover thermal analysis also as part of this course, because then it would amount to uh, so much other theory that has to be covered as part of thermal analysis. Okay, so the second question is, these days high frequency rotor cells are being developed. What is the current development in India? Yeah, so of course, this again is if you are asking with reference to the finite element analysis. In fact, one of my PhD students, she is working on analysis of insulation degradation in photovoltaic modules, and she is actively using finite element method to analyze the insulation degradation associated with solar photovoltaic panels. So again, you can see such knowledge on finite element method is useful not only for traditional devices like transformers, motors, generators, but on on the equipment related to solar photovoltaic or maybe wind and all the renewable energy sources that are going to be increasing in the power system. Such analysis would be useful. Okay, and one more question is how you relate phi with V in the course. Okay. So actually phi, I'm sure you are asking phi as a voltage variable, if I am not mistaken. So voltage and phi, when phi is used as a voltage, phi and V both mean the same. Small v is reserved for velocity. Capital V is for voltage, and sometimes phi is also either phi is used as a flux variable in magnetostatic or magnetic field analysis. But if you are using, if you are want to explain in general some partial differential equation involving some scalar, like for example, Laplace equation or Poisson's equation, you generally would say del square phi is equal to minus rho upon epsilon, like that. So there phi is a scalar variable, and that scalar variable phi can incidentally be a voltage variable. So I hope I answered your question. Mr. Chandrasekhar, I hope your query is answered. Yeah. Okay. Any other question? So I request you to give also some feedback. Okay, thank you for saying that you understood. Thanks. So I also request participants to basically give some feedback. Suppose if there are some typos or some mistakes while delivering the course, or something is not very clear, that feedback can be given on email. My email is I think I can give you the email address. I can type here. I think it is there on the net, but still I will type it here. You can always write to me on this and give your suggestions, feedback, right? So okay, now the next question is FEMM a good software to begin? Yes, yeah, it is definitely a good software, and in fact, many industry guys, I recommend this software because it is a freeware. And in fact, there are some, on my website, um, I have given some FEMM based tutorials. So can actually Grishma or Sairam, which top tutorial I'm talking about, that leakage inductance. Can you just
Yes.
find out that link on, I think, that FCL website somewhere it is there, and can you paste it on the chat box so that they can see one or two FEMM based tutorial problems. So other thing is, yeah, well, there is one comment by Bharti madam that feedback. There is a weekly feedback on, and there is a discussion forum too. So okay, we will see those points in that weekly feedback forum, and if there are some suggestions, I will. Next question by Mr. Paul Christian is, sir, whether some practical application examples be covered in the course? Yeah, definitely. From lecture 21, 22 onwards is all practical case studies are covered. All practical problems are solved, right? From, insulation design in high voltage equipment to analysis of eddy currents to some non-linear problems, then some coupled circuit field problems include involving transients in systems, and finally I think torque and force calculation. So all these are all practical problems. Now the problems that are solved and analyzed may not be exactly what you want to solve, but they are representative problems, and then you can basically understand how they are solved, and then you can apply the theory and knowledge to your problem. Yeah, so any of my colleagues, Sairam, Grishma, or Swapnil, they can also, respond to any of the questions if they have some additional points.
Yeah, sir, I would like to add one point about
Yeah.
thermal analysis.
Hmm.
So, one interesting thing is like if you understand differential equations properly,
Hmm.
so diffusion equation in magnetic field analysis and diffusion equation of thermal analysis are similar.
Yeah.
So if they understand how to solve diffusion equation from our course, they can apply the same code for thermal analysis.
Exactly. Only variables will change.
Only variables will change, but one difference is like uh, they in case of thermal analysis there is something called as convective heat flux. We have to apply convective heat flux, so
Yeah.
it's a kind of a Neumann boundary condition.
Yeah. So in thermal analysis, boundary conditions are a little bit tricky. They are not as straightforward as in
Yeah,
electromagnetic.
similar to our electromagnetic analysis, they will be like declared boundary condition for constant temperature boundary and Neumann boundary condition for convective heat flux. So, Neumann boundary condition that we have explained in that one lecture, no, H tangential H applying tangential H field for that mitad joint.
Hmm.
So that same formulation can be changed. It cannot be used directly, but it has to be changed appropriately to do that to do that convective heat flux as well.
Yes, I agree.
Yeah.
Yeah, so see, thermal basically the one more tricky thing in thermal analysis is those, empirical constants like
Ah, yeah.
convection and all that.
Hmm.
So that, those kind of, issues are less in electromagnetic analysis. So that's why a thermal analysis has to be done with, with the help of some, expert who has good experience, in terms of using proper empirical constants and all that. If those are properly fed, then it is a straightforward analysis. Yeah, then next is one by one Nikki S. I'm not student but deeply interested in electrical engineering. Is it possible that I can access the experiment? I think you are asking whether you can see the yeah, you can always watch videos and upgrade your knowledge. Uh, that is possible because they are all on YouTube. Again, question by Paul: would it be helpful if some contact? It would be also helpful contact details are shared to discuss difficulties in future using FEM in commercial software. So that see if there is some generic problem related to this course, we can definitely help you. But if there are some specific problems in that you face while using a commercial software, I think it is best if you address it to that software company, because there are many. I'm sure these days there are those what they call user groups are there, and there are email addresses, and there is this combined shared group. So you can post your query on such groups, and you will get answers, or you can directly ask for help from the commercial software. But if there is some generic fundamental difficulty that you face, while understanding this course or something, you while doing a commercials, using a commercial software, if you relate it to what is taught in this course, and if you have doubt with respect to that, we'll be happy to, sort of, help you with that. Okay, so any further? So, Dr. Gishma, did you find that link, FEMN?
I have shared it.
Where did you, okay, you already shared it. Okay, okay,
I
fine.
shared it with Bharti madam to.
But it
Okay.
is not okay, but
You
it is
can
not visible.
type in chat box, no? You have also access to chat box, right? You can type it in chat box.
So because I am not able to see, because madam has already written the link shared by Dr. Sairam, but it is not shared.
No, actually, you have to open. No, I am also not able to see, but if you can type in chat box, where you able to see my
YouTube.
YouTube chat box?
Yeah, YouTube chat box. It already shared.
Already shared, she's saying. Okay, fine. Okay, it is 18:28 now, so almost 1 hour now. So we have been discussing. So if the, yeah, yeah, so there is a comment, finally, positive comment from Mr. Paul Christian, that thank you very much. You have explained complex EM and FEM theories in a very easy to understand manner. So I actually also, suggest you to do two things. One is, along with this course, you read um, this my book on electromagnetics, which is, co-authored. I have adapted that book by Professor Sadiku, and you can go through that. Particularly, there is a chapter on finite element method, chapter 15 there. So it explains finite element method in a very simple way. And the electromagnetic theory, you can go through that book and understand better. There is one more thing, that there is a what is known as virtual electromagnetic laboratory, which I think I have mentioned in the during the one of the lectures of the course. But it has got many software experiments and true field plots and some kind of parametric analysis. The many concepts are explained there. So I will again just copy that link in the chat box of. So some of you who are interested to, I have just pasted that link of that virtual electromagnetic laboratory (VEL) in the chat box. So you can also go through some of the experiments there. You can actually vary some variables and see the effect of field. Understand, and here, of course, both low frequency and high frequency, both in fact topics are covered. And in fact, high frequency electromagnetics is covered more, I should say, in this, because there are many concepts in high frequency electromagnetics as compared to low frequency. So you can actually, take help from there. So I think if, before closing, maybe Mr. Soptil, if you want to add something more, and I want to especially thank you for, um, you participating in this, live interaction and sparing your time. So maybe you want to.
No, my pleasure, sir. I mean, electromagnetics, as already mentioned, it's not that straightforward area. People usually, tend to make a lot of assumptions, before jumping into electromagnetics. But I think with proper coursework in electromagnetics and FEM, uh, I think we can definitely, conquer those software tools plus the real life electromagnetic problems. Sometimes we may feel the learning curve is steep, but I think we just have to be patient and give some more time to these basic concepts, spend more time on the tools, spend more time on the theory part. And I think we shall be in a good shape to tackle some of these problems.
Okay, thank you. So I think we can close here, but again, I would like to request all those, who have registered for this course. The next interaction would depend on your interest and questions that you may please send some questions or queries in advance, and we will take those queries and questions in the second interaction, which will be more or less at the sort of fag end of this course. So please, we look forward to your comments, queries, questions on specific topic. Today we had general discussion because the course has just started, but next time we will take some specific, queries and, we'll try to address those. Okay, so happy learning electromagnetics and finite element method. I think we can close. So I thank also Dr. Sairam and Dr. Vishma for helping me actively throughout this course, and while I was recording this course, both of them have tremendously helped. And now you can see they are now faculty members in the reputed institute. So working in this area is definitely rewarding. So for those who are trying to decide the career option. Okay, Bharti madam, can we close? I think we can close this session. Bharti madam and NPTEL team, you can close this from your end, please.
Okay, sir. Thank you, sir.
Okay.